Hi everyone, welcome to Oral Electronics session number 18. So we'll continue with some more problems in inverters, and then we'll close the inverters, and then we'll go on to the next topic is DC to DC converters. So next question is given like this: in single pulse modulation of PWM inverters, the pulse width is 120 degrees. For an input voltage of 220 volts, what is the RMS value of output voltage at the fundamental frequency? Yeah, this question is related to single pulse modulation technique. Here we need to calculate fundamental voltage RMS value. As we know, we already discussed. So V01 we discussed already, but again I'm telling that RMS value of the fundamental voltage in case of single pulse modulation technique is 0.9 VDC into sine d by 2. Okay, so now substitute the values like 0.9 into 220 into d is given 120 divided by 2 sine 60 is nothing but root 3 by 2. Okay, so this type of question is given in the GATE exam 2 times. Okay, so that means other than this one I'm talking about. So remember, we need to answer this question, either you need to remember the equations what we discussed, or otherwise Fourier series. If you know the Fourier series, we can derive that what you want. So the required voltage is here 171.47 volts. Okay, move on to the next question. So the single phase full bridge VSI shown in figure has output frequency of 50 Hz. That means output frequency it is running with 50 Hz. It uses unipolar pulse width modulation with a switching frequency of 50 kHz and modulation index of 0.7. For V in input voltage, DC voltage is 100 volts. Inductance, filter inductance, this is filter. So inductance is 9.55 millihenry, capacitance is 63.66 microfarad, and resistance, that is the load, 5 ohm. The amplitude of fundamental component in the output voltage V0, that is nothing to here, under steady state. So we need to calculate output voltage fundamental component. Okay, amplitude is nothing but maximum value after the filter. That means here you can see that, so this is given, this is the actual output of the inverter VR. So this is actually filter to filter out the harmonics. Okay, and this is the load. Now we need to calculate the load voltage. Actually it is a low pass filter, means it will act like that means if you take that filter waveform, so if it is assumed some corner frequency will be there, it will allow all the frequencies below the corner frequency, and above the corner frequency it will attenuate everything around. But this is a practical filter, that means strictly speaking it should attenuate all the frequencies except the 50 Hz frequency. Okay, 50 Hz, that means that's a fundamental component, that's a required component. It should not actually attenuate that one. But here this is a practical filter. So practical filter, whatever the component is there that is actually required at the voltage will also be attenuated a little bit. That means if you take the practical filter waveform, it will be something like this. Okay, so that means apart from the unwanted frequencies, required frequency component also will be little bit impacted. That impact we need to calculate. Okay, so now first thing, it is actually like unipolar pulse width modulation. Unipolar pulse width modulation is there, means that is related to sinusoidal PWM technique. So first thing is we need to calculate what are the input, like from the inverter side, what will be the required output is there. That means here VR is the output voltage of the inverter before the filter. So that we will take it as a like VR output voltage and fundamental voltage. Okay, 0, 1 max value. Okay, so That means output voltage of the inverter fundamental component max value. That we have the relationship. What is the relationship? Modulation index multiplied with source voltage VDC. That we already discussed in the sinusoidal PWM technique. Now you can substitute that 0.7 modulation index is given, that's a 0.7 multiplied with source voltage is 100. So that means 70 volts is the maximum value of the fundamental component. Strictly speaking, if this filter is ideal, the 70 volts as it is need to be appear here, but because of this practical filter, this will be little bit disturbed. That is what we need to calculate. Now we calculated whatever it is required from the inverter side. That means from the inverter side we calculated using this equation. Now it is like a kind of, from this onwards, it is nothing but like a kind of circuit theory. Circuit theory is nothing but for this input we gave that 70 volts, or what will be the output voltage. So that you can calculate using voltage division formula. That we can calculate like this. So that means V0, that is the required output voltage after the filter, 1 max. That is the output voltage. That is nothing but voltage division formula. This is Z1 and this entire thing is actually, you can take it as a Z2. Okay, so that is nothing but in total voltage, that is nothing but VR01 max multiplied with required voltage impedance, that's nothing but Z2. Z2 is nothing but, here it is nothing but like we can calculate the Z2 later, leave this one, Z2 divided by Z1 plus Z2. So that is what you can calculate using the voltage equation, voltage division formula. But what is Z2 here? That we need to calculate now. So Z1, Z2 we need to calculate. So Z1 is nothing but, it is, okay, you can use the X or whichever the way we can represent. So this is nothing but J omega L, that we need to calculate. And Z2 is nothing but, it's a parallel combination of resistance and capacitance, that we need to calculate. That is nothing but, so it is like R into 1 by J omega C divided by R plus 1 by J omega C. Okay, 1 by J omega C. We need to calculate those things. After substituting inductance value, capacitance and resistance, we can get Z1 is J3 and Z2 is like this. Now if we can actually try for V0 max by replacing all the values in this equation. So you can get V01 max equal to, so R01 max is 70 volts we calculated, multiplied with 5 divided by this one, 1 plus J 0.0, approximately you can take 1, so divided by Z1 plus Z2. Z1 is J3 plus, again Z2 is 5 divided by 1 plus 1 plus J.01. Okay, so that will be equal to, so 70 into, because LCM we can take this one and this one gets cancelled, then it will be 5 divided by, so 1 into J3, it remains J3, okay, minus J multiplied with J minus 1, so that means it will give you almost 0.03 plus 5. So that gives approximately 62.7 volts, 77 volts. So this is the answer. Okay, to calculate this, you need to take that magnitude of this one, 5, and you need to calculate root of 3 square plus this square. We need to get that. That is the answer for this one. Again, I am telling that you can go to the circuit diagram. Using the PWM technique, you can calculate output of the inverter. Output of the inverter based on this one is only fundamental value like this. After that, circuit representation, so that circuit diagram, using that circuit diagram, using your circuit analysis formulas, you can calculate based on your understanding also, not necessarily need to follow the same way. Okay, so that is the answer for this. Moving on to the next question. So the switches T1 and T2 in figure A are switched in a complementary fashion with sinusoidal pulse width modulation technique. This is a pulse width modulation technique. So you can see that. Now modulating voltage means the sinusoidal waveform which is compared against the triangular waveform is also called as a modulating signal. That is given 0.8 sine 200 omega t. That means magnitude of this waveform is 0.8. and magnitude of the triangular or carrier waveform is already given 1. So modulation index you can take 0.8 and carrier shown in figure B. The carrier frequency is 5 kHz and the peak value of the 100 Hz component of the load current is, remember, if you look at the modulating signal frequency, that is the output voltage frequency. Modulating signal, nothing but sine wave frequency, that's what we are expecting at this one. So that's why you can see that this sine wave frequency is nothing but 200 omega, 200 pi t. That means omega is here 200 omega is nothing but, you know, like what is that, 2 pi f. F is actually, using that equation, it is 100 Hz. That means here fundamental component is nothing but 100 Hz. Okay, fundamental component. So here we need to calculate the fundamental component of the load current. So what are the formulas we have? So you can use that, you can calculate here also, not an issue. So we calculate one by one. Fundamental voltage, so I01 max, because it is given and asked about peak value. Okay, that equal to, how to calculate, V01 max divided by Z1, because it is a fundamental component, we need to take Z1 because load is RL load here. You can see that load is RL load. And this inverter is half-bridge inverter. So that is also we need to look at that. So but to calculate this, we need to know that what is the V01 max, what is the Z1. Z1 we can calculate from the load and we need to calculate the V01. V01 max we can calculate from the sinusoidal PWM technique. What is that? That is nothing but modulation index multiplied with VDC by 2, that is nothing but source voltage divided by complete source voltage divided by 2, because it is a half-bridge inverter. So you can substitute now and get that. Z1 you can calculate from here and substitute here, you can get the answer. So that means here you can actually calculate Z1 using this one. So omega L is given 16 ohm and 100 Hz. 100 Hz means there's a fundamental component. That's why no need to worry about anything. This is a 12. So that means Z is nothing but root of 12 square plus 16 square. So that is nothing but here 256 plus 144. That's a 400. 400 root under root is nothing but 20. So this is 20 ohm. Likewise, you can calculate V01 max, that is equal to modulation index 0.8 into total source voltage divided by 2. So already given VDC by 2, already given as a 250. Or you can take that to 250 plus 250, 500 divided by 2 again 250. So you can take 250. Okay, so 0.8 into 250 is nothing but 200 volts. Now using this you can calculate I01 max is V01 max 200 divided by Z1 20, that means 10 ampere. So that's what. Okay, so here we need to calculate the load current max value for the fundamental frequency. That means peak value of 100 component, 100 Hz component, nothing but that's the fundamental component frequency. How to get that? That we need to look at the modulating signal. That frequency is same as the load frequency. Okay, so remember two things. Load frequency is always by the modulating signal frequency, and carrier frequency signal is nothing but switching frequency, the switches at which those will be turning on and turning off. That is what. Okay, so that is equal to V0 1 max divided by Z1. Z1 we can calculate from the load, and V0 max can be calculated from the PWM technique using this equation. Okay, so substitute everything and then get the answer. That's it. Move on to the next question, and this is the last question for the inverters. So look at here. Here also given average inverter. Okay, but total full voltage is given 2 times VDC. Okay, remember that. In our case, this is VDC equal to 2 times VDC. Remember that. The figure below shows a average voltage source inverter supplying RL load. Yes, again it is RL load. Okay, of the RL load with R equal to 40 ohm, L equal to 0.3 by 5 Henry. The desired fundamental frequency of the voltage is 50 Hz. Okay, look at that. Frequency is 50 Hz. The switch controls signals of the converter are generated using again sinusoidal pulse width modulation technique. Okay, with the modulation index 0.6, this is required for us. Okay, at 50 Hz, the low RL load draws an active power of, that means active power of 1.44 kilowatts. The value of DC source VDC we need to calculate. That means we need to calculate what is this value. Okay, if you know that total 2 VDC, we can calculate that. That 2 VDC we are taking as a VDC only. Okay, or directly we can take it as a like a kind of, in our case, what's that? VDC by 2. VDC by 2 is nothing but VDC. V capital DC. Okay, from this one. If you want to calculate the VDC, means we need to calculate VDC by 2 from our original equation. Okay, we'll do that. So how to analyze this equation, this problem, we will see one by one step. Okay, look at here. What is given? Active power supplied or consumed by the load at 50 Hz is given. That means that power is only supplied by the fundamental component. That's the meaning of that. At 50 Hz means there's nothing but power supplied by the fundamental component. That is nothing but I01 RMS value square into resistance. This is not the total power drawn by the load. It is only power drawn by the load at 50 Hz. That is nothing but only by the fundamental component. If suppose it is total, means we need to take I0 RMS, not the 1. So that's what. So from this, resistance is given, power is given, we can calculate the I0 RMS. Once we know this, we can calculate like V01 RMS voltage. V01 RMS voltage is nothing but I01 RMS voltage into Z1, because it is an inductive load. So voltage, fundamental voltage, sorry, this is not the maximum, this is RMS value. Okay, we are talking about RMS values. Okay, V01 RMS value equal to I01 RMS value to Z1. So once you got this one, then we can calculate V01 max. All are sinusoidal waveforms, then V01 max value. How to calculate the max value from the RMS value? It is nothing but root 2 times RMS value. Okay, so that's what. So once you got that, then we have the equation from the sinusoidal PWM technique, that is nothing but V01 max equal to modulation index multiplied with VDC by 2 in case of average inverter. So this is what. So once you know this one, then you can calculate. That is actually in our equation is V capital DC. So that is what we need to calculate. So now we need to substitute in the top to bottom order. Once you substitute those, you can get the answer. Okay, I'm taking those equations what we discussed and substituting everything in this, and then we can get the required things. So from this we need to calculate I not 1 RMS value. How to calculate this? It is root of, so first we need to take the R this side and apply the root. That means root of P1 divided by R. Okay, P1 is given, what is that? 1.44 kilowatt. That means 1.44 kilowatt multiplied by 1000, then you will get. Resistance is given, it is 40 watts, sorry, 40 ohms. If you take 40 ohms, then it will give you directly current is 6 ampere. Okay, that's what. So now substitute here, then get the V01 RMS value. V01 RMS value is nothing but it is I01 6 into Z. Z1 is nothing but we need to calculate the impedance at fundamental frequency. That's nothing but 40 square plus L is given 0.3 by pi. So 2 pi f, that means 2 pi f is 50 H into L. L is nothing but 0.3 by pi whole square. Everything is under root. So then we need to get this one. So pi gets cancelled. Okay, pi gets cancelled. Then this will be multiplied with like a 15 into 0.3 means this is actually 3 into 5, 15 into 2, 30. So 40, 30. So that means it will actually give you 50. So that means like 6 into 50. So RMS value of the fundamental voltage is 300 volts. Now we need to get the max value. So what is the max value? Max value is nothing but V01 max is 300 into root 2. So leave like that. Then we need to calculate, okay, I'm directly taking VDC. So VDC from this equation, VDC equal to, so that is nothing but max value divided by modulation index. That's nothing but 300 into root 2 divided by modulation index is here 0.8. So that gives you, here it is 500 root 2 volts. Why I'm actually leaving in this root 2 is the options are given in this way only. Okay, so that's the answer. Okay, so VD is equal to 300 root 2 divided by modulation index. Modulation index is given 0.6. If you take that means totally you will get this one. So that's the answer. Okay, so thank you, and stopping with this. If you have any questions or something, you can send me the mail, or otherwise you can send as a comment. We can discuss. Thank you.